Hello and welcome to Sadamatica. In this video, we would look at how to solve systems of linear ODEs. This is the first video on revision of dynamical systems. Without wasting much time, let's get started. So we could recall that when we have this given differential equation, dx dt to be equal to, let's say, ax. Now this differential equation, yes, it is ordinary because the derivative is ordinary derivative, and then it is autonomous in the sense that the right hand side is made up of only the dependent variable. So this differential equation is also autonomous. Now when we look at the general solution, so in order to solve this, let's quickly look at how to solve it, or let's revise or remind ourselves on how to solve this. We have the x over x here to be equal to our a dt here. So this gives us what? The integral of 1 over x dx to be equal to the integral of a dt. Then this gives us the lim of x plus a certain constant, but then I would like to move all my constants to the other side, so this becomes equals at plus what? A certain constant c. So the summation of the two constants is still a constant, so we have that. Now this now gives us, we want to find the unknown function x of t whose derivative will give us ax. So in order to do that, I'll have to take the anti-logarithms of ln x. So this gives us x to be equal to e to the power at plus c. Then this becomes x of t to be equal to what? E at dot e what? C. Now e exponential constant is still a constant, so we have x of t to be given as a certain constant k e at. So this becomes a solution, or the general solution of this given differential equation, and we know that this differential equation is autonomous. So because of that, this gives us an idea of how the solution of autonomous homogeneous differential equations look like. Now let's consider this system of differential equation. The x1 dt to be equal to a1 x1 plus a2 x2 plus a3 x3. Then the x2 dt to be equal to b1 x1 plus b2 x2 plus what? b3 x3. And the x3 dt to be equal to c x1 plus c1 x1 plus b2 c2 x2 plus c3 x3. Now we were told, or we know, that in order to solve systems of equation, an easier way is to rewrite them in a matrix form. So in doing that, implementing that here, we have d dt for a certain column matrix x1 x2 x3 to be equal to our coefficient matrix a1 a2 a3 c1 c2 c b here b3, and then c1 c2 c3. Now that being said, I'm writing out x1 x2 x3 here. Now that being said, we can represent this column matrix here by a certain matrix, a certain value a. So we could rewrite this as, let's say, dt of certain x this way, and then write the coefficient matrix as something like this, and then have our x here as well. Now writing this way, you realize that this looks a bit more like our differential equation that we solved earlier. So which means that this would give us an idea of how the solution will look like. So referencing from here, we could say that our solution would look a bit more like x of t will be given as a certain constant k e to the power of the matrix at. But then it is absurd to have your power as a matrix, or to write an exponent, a matrix as an exponent. So in order to solve this, then we would have to use some important things in the matrix. So I call them important things, important ingredients of the matrix. That's the eigenvalue and the eigenvectors v. So the eigenvalue lambda and the eigenvector v of the matrix A. Now once you get those things from the matrix A becomes useless, or once you remove those things from a matrix A becomes useless, because actually the eigenvalue and the eigenvectors have the relevant stuffs of the matrix, so and represent them here. So it means that our solution will look a more lot like this. We have k here and then the v e exponent the lambda t. Now this should give us an idea, or this should be how our system or the solution should look like. Okay, now considering that, so let's recall from the solution we just did. Let's write it on top here, and then so we said that our solution should look like this when we are done. Certain constant k e exponent, the eigenvalue times e exponent the eigenvector eigenvector times e exponent eigenvalue t. This should be our solution when we are done solving the system. Now let's consider this example and see whether we would get something like this. Now given the derivative differential equation dx dt to be equal to 2x plus 3y, and what another equation dy dt to be equal to 2x plus y, it means that we could have, writing this in a system form, would have the x1 dt is equal to 2x plus 3y, and then we'll have dy dt here to be equal to 2x plus y. That being said, we can rewrite this nicely as d dt of xy here to be equal to 2, 3, 2, 1 times the column matrix xy here. Now that being said, it means that we can now try to find the eigenvalues of this matrix. So to find the eigenvalues, we recall that what? To find the eigenvalues, all we need to do is to find a certain matrix where when we subtract the eigenvalue from that and the multiply by the eigenvector, will get 0. But then our eigenvector shouldn't be trivial. For that matter, we would have to find the matrix whose determinant, after removing the eigenvalue from it, we would get 0. So doing, we would have our 2 minus lambda here. Sorry, you have to change the notation. So we would have, let's say, the absolute value, which is the determinant of 2 minus lambda, then 3, and then 2, 1 minus lambda here, times what? So this should be equal to 0 when we are done. This implies that we would have 2 minus lambda times 1 minus lambda minus what? 2 times 3 to be equal to 0. This gives us what? 2 times this becomes 2 minus 2 lambda minus lambda plus lambda squared minus 6 equals 0. Simplifying this would have lambda squared minus 3 lambda minus 4 is equal to what? 0. Now, when you solve that if you solve that quadratic equation, we would have our lambda 1 to be given as what? 4, and then our lambda 2 to be given as -1. So you can try this, either use a calculator to solve it, or you solve it with your head or something. Now, after getting this, we now have to find their corresponding eigenvectors. So in order to do that, let's say finding the vector v1. So for v1, let's do this way. Now for lambda 1 to be equal to 4, we should let the eigenvector 1 to be equal to a certain one a, let's say m1, m2. Then we can recall this equation here as what? A minus our lambda is 4, so 4i, then times our v1. This should be equal to 0. So it means that we would have something like this. Our a, which is 2, so that's 2 minus 4, 3, and then 2 here, 1 minus 4 here, times what? Our v1 is given as m1, m2. We said it should be m1, m2. This should be equal to 0, 0 here. Now, from here, we could have, writing this in augmented matrix form, here becomes a -2 here, 3 here, 2 here, -3 here, and then here becomes 0, 0 here. Now, we can easily solve this using Gaussian elimination. So, this becomes what? We just have to do, so our new root 2 will now be equal to 2 plus what? Root 1. This becomes -2 here, 3 here, then so 2 plus -2 becomes 0, and then -3 plus 3 becomes 0 here. We have 0, 0 here. Now, rewriting this in an equation form, we have -2 here, m. So let's do it like this. So this becomes what? We have -2 here, 3 here, 0, 0 here. We have our m1 here, m2 here. This should be equal to 0, 0. So which means that if we should rewrite this in an equation form, we would have -2m1 plus 3m2 here should be equal to what? Should be equal to 0. Then that's all. So which means that equation 1 depends on m1 and m2, but then we don't know m2 here. So from here we could say that our m2 is what? Arbitrary. Our m2 here is arbitrary. So which means that we would have to choose a particular m2. Now the question is, how do we choose m2 and from which value do we choose m2? So the best way, or one way of choosing our m2, is to consider what? Consider the natural basis. So the natural basis E1, which is 1, 0, and then E2, which is what? 0, 1. That's for 2 by 2 matrix. Now when we consider this natural basis, we would have to choose a value for m2 such that what? Choose a value for m2 such that our v is what? Not equal to 0, which means that it's not trivial. So now when we realize, when we choose our m2 to be 0, putting 0 here will make the whole of this also 0, which means we'll have 0, 0. So it means that we can't choose our m2 to be 0. So instead we have to choose this one where our m2 is what? 1. So when we choose m2 to be 1, we realize that our v1 won't be what? Arbitrary. So in doing so, we have what? we have in doing so we have, so we choose our what, m2 to be equal to 1. When we do that, then we would have our negative, so negative 2m1 plus 3m2. So negative 2m1 plus 3m2 should be equal to what? 0. But our m2 is that, so which means that we have negative 2m1 to be equal to what? Negative 3. So our m1 is equal to 3 over 2. Which means that we can conclude that our v1 here should be equal to what? 3 over 2 here and then 1. Okay, so this is, now one more thing that I like doing is that after getting the eigenvector for lambda 1, which is equal to 4, I write my first part of the equation, the solution. So which means that the solution 1 should be equal to what? A certain constant k, right, times the vector v1, the eigenvector v1, then e exponent the eigenvalue 1 times t. So this should give us a certain constant k, then what? v1. So our v1 is giving us what? 3 over 2, 1. And then e exponent what? Our lambda 1 is 4. So this should be our first part of the solution. So x1 should be equal to k, 3 over 2, 1 here, e40. Now let's find the eigenvalue for the, you can pause the video and try finding the eigenvalue for the second one. So for lambda 2 equals what? Negative 1, right? Let's what? Our v2 to be equal to a certain n1, n2, right? Such that what? Our a minus 1 becomes plus, so plus lambda v2 should be equal to 0. That being said, we would have what? Our a is giving us what? Our a is 2, so that will be 2 plus 1, 3 here, and then we have 2, then 1 plus 1 here, times our n1, n2 here to be equal to what? 0, 0. No. So this implies that we would have what? 3 here, 3 here, 2 here, 2 here. This is quite simple. So writing it in augmented matrix form, straightforward. Here we cancel 0, 0 here. So solving that, you know that solving this, we can simplify this by dividing through row 1, and then 1, 3, row 1, then half row 2. So this becomes 1, 1 here, 1, 1 here, 0, 0 here. Okay. So this should give us what? In order to do that, we just have to do what? Our new row 2 will be giving us the old row 2 and that's what? Row 1. And this is what? 1, 1, 0, 0, then 0, 0. Now rewriting this in our normal matrix form, we have 1, 1 here, 0, 0 here, and then we have what? n1, n2 here, and then this is equal to what? 0, 0 here. So that being said, we remember that we said we would have to choose a certain n value. So if you have n1 plus n2 to be equal to 0, we would have to choose a certain n value here such that this whole equation doesn't give a 0, 0. So considering the natural basis, v1 should that's 1 0, and then e2 that's 0 1. We choose what our n2 to be equal to 1. Then we would have our what? If we choose our n2 to be equal to 1, then it means that we would have our n1 to be equal to what? Negative 1. That being said, this implies that our v2 will be what? Negative 1 at 1. Alright, so if we have our v2 to be negative 1, then all we have to do is to say that our x2, the second part of the solution, should be giving us what? Our x2 should be giving us a certain constant k2 here times v2 e exponent lambda 2t. This gives us what? This gives us our eigenvector. So this gives us k2 here times our eigenvector negative 1 1. Then e exponent our eigenvalue here is our negative 1. So e exponent negative t as the second part of the solution. Now we know that from the principle of superposition of solving differential equations, if we have the differential equation giving us two solutions, then the linear combination of those solutions is still a solution of the differential equation. So by so doing, it means that we could have a certain our x of t should be equal to, let's say, x1 plus x2 as our solution. Obviously I would have brought a constant here, but then the constant times, okay, I can bring a constant here, but then the constant, so let's say c1 here, c2 here. Now the constant times the constant will still be a constant, so don't worry about that. Now we record our x1 was giving us what from our previous slide. Now x1 is giving us this, so k 3 over 2 e, so we have k 3 over 2 here 1, then e exponent 4t. Then our x2 is giving us a certain k2 here, so it's a k1, certain k2 here, then negative 1 1 here, e exponent 1 negative t, e exponent negative t here. So from the principle of superposition, it means that our solution should look of this form: x of t to be equal to what? A certain k1 times, so c1 k1 is still a constant, so we can recall it c1, then this, so that will be what? Times 3 over 2 1 here, e 40 plus c2 here, then times that negative 1 1 here, e exponent negative t. So this is our solution to the given system of differential equation here. Sorry, where is it? This is our solution to the given system of differential equation here. Now, when given, to find the value, so this is a general solution, so general solution. So it's a general solution because what? We don't know c1 and c2, but then you'll be when we are given, let's say, some initial conditions or boundary conditions, then you can find the value of c1 c2. By so doing, we would have a particular solution for our differential equation. So let's look at the second example, and then let's see whether you can solve this example. So what if we are given this system of differential equation x dt to be equal to what? X plus 4z minus y dy dt to be given as what? 2y plus 3x minus z, then the z dt to be given as what? 2x plus y minus z. And we are asked to find the solution of this system, the general solution of the system above, of ODEs above. How do you solve it? So you can try this question on your own, and then when you are done solving, you move to the next video to see how we solve this particular question. Thank you.